Hi everyone, and welcome back to Big Picture Technology and Science. This time we'll solve a mixed circuit. A mixed circuit is a circuit in which you have both parallel and serial connections. And as always, we'll start with 60 seconds of theory, some intuition, and then dive into the problem. Okay, so let's remember the formulas that we've learned regarding serial and parallel circuits. Let's look at a serial circuit. The voltages in a serial circuit add up. So when you add up the voltages over the different resistors, you get the battery's voltage. The current is the same throughout the circuit. Doesn't matter wherever you check, you get the same current. And that's because charges don't disappear when they flow through the circuit, and the equivalent resistance of a serial circuit, you get it by just adding the different resistances. When you look at a parallel circuit, voltages are the same, they are equal over the different branches of the parallel circuit. The current adds up. When it arrives at a junction, it divides between the different branches, and then it adds up back into the total current of the circuit. And when you look at the equivalent resistance, that's the theoretical formula, but it's not the one that you typically use, because there's a simpler derivative of this formula for two resistors, which is this formula here, down here, and an even simpler one when there are two equal resistors in parallel. You simply get an equivalent resistance that's equal to half of each of the resistances. And of course we have to remember Ohm's law. Ohm's law, U equals I times R, is going to be very handy throughout our studies. So before we move to the question, let me try to give you some intuition into one of the more confusing aspects of equivalent resistance. How can it be that when adding resistances in parallel, the equivalent resistance drops and not increases? Let me try to give you some intuition into that. Now imagine a group of students. I'll try to draw 4 of them here. Sorry about my limited drawing capabilities. I'll draw 4 of these students here. And these students have to move through a corridor. The corridor would serve as our resistor. Now, when they move through the corridor, they'll have to they'll have to do some squeezing into the corridor. They'll have to spend some effort and some time, but they'll finally get it done and flow and move through the corridor. Now, imagine what happens if I add yet another similar corridor in parallel to the original one. What would happen to the group of kids or of students? Would it be easier or harder for them to move through the 2 corridors now? Well, if you think about it, it would be easier, right? Because they would now have the option to choose between the 2 corridors. They could either move through the original one or through this one. Some would choose the first one, some would choose the second one, but they'll have less squeezing to do and less effort in order to move through the two corridors, as compared to the single corridor at first. So as you can see, 2 corridors in parallel are easier to flow through than one corridor. And that's a pretty good analogy to connecting 2 resistors in parallel. Now, tricky questions. What would happen if I would add yet another but very, very narrow corridor in parallel to that one? That is a very big resistor in parallel to these 2 resistors. What would happen to the equivalent resistance of this whole structure? And yes, as you suspect, even a very big resistor in parallel would still serve as yet another way through which some of them could run, and therefore even a very big resistor in parallel would still reduce the equivalent and overall resistance. Okay, so let's look at today's questions. They were asking us to calculate the circuit's equivalent resistance, to calculate the circuit's total current I, that's the current that flows here, and to calculate the voltage between various pairs of points in the circuits, A, B, C, and D, and so on. Let's start by calculating the circuit's equivalent resistance. As you'll see, calculating equivalent resistance is somewhat like peeling an onion. You start from the outside and you make your way inside. Unlike peeling an onion, it makes a lot of sense to keep the different layers that you go through. So let's start by checking how can I start to simplify this circuit. And the first thing that jumps in front of me is that R4 and 5 are connected in parallel, and therefore, because they're both connected to the same junctions, C and D, and therefore they can be simplified into a single resistor according to a formula of equivalent resistance in parallel. So that would definitely be my first step for simplifying the circuit. I want to save time and I don't want to copy the circuit by hand again, so I'll copy whatever I can and then simplify the other parts by hand. This part doesn't change, so I'll copy it and I'll paste it here. You'll have to copy it. You'll have to copy it again. You don't have this, but that's not such a big deal. That's it. So let's replace these two resistances by a single resistance. Let's call it R45. So I still have R2. That's R2. That's R1. And I'll replace these two with a single resistor. I'll call it R45. Okay. I'll call it R45, and I'll calculate its value. Okay, now I have it connected to the circuit. I call it R45. And what would be the value of R45 since they're connected in parallel? I'll use the formula for connections in parallel, and I see that they are both have the same value. So it takes me here, and I see that when you connect two resistors, equal resistors in parallel, the equivalent resistor would be half of the original value. That makes it R kilo ohm. For my convenience, I'll keep points C and D. I'll keep these, even though they are not junctions anymore, I'll keep these here, so I'll have a future reference. Okay, let's keep peeling the onion. What would be our next step? We are now looking at this new circuit that we have here. Looking at it, we can see that the next layer will probably be connecting these two. Since they are connected now in serial, we can simplify this circuit by turning these two into a single resistor. Let's draw another yet simplified version of the original circuit. Again, I'll take some of it, so I won't have to draw it. Again. It's this one. I'll paste it here. You'll have to draw it. You will have to draw it again. And now I'm connecting. Just so you'd see, I'm connecting these two into a single resistor. I'll name it R245. It's now equivalent to three resistors. Let's draw it. That's our new resistor. It's R245. And what would be its value? It's the serial connection of two previous resistors. One equals 4 and the other equals 48. We use the rule for connecting resistances in serial, and R245 would equal 4 plus 48. That would give us 50. Sorry about that. That would give us 52 kilo. I'll just make sure that all the data is here. That's R1 and it equals 20 kilo. Okay, let's go on. I hope you're not too tired. I think we have another 2 steps to go. Looking at the new circuit that we have here, how do we continue simplifying it? Well, probably you can see that now we have again 2 resistors connected in parallel. They are both connected to the same junctions, A and B. It's our new combined resistor R245 and the original resistor R3. Let's combine them into a single resistor by applying the parallel equivalent resistance formula. I have to draw yet another circuit. We'll call it C. I'll try to squeeze it here. Hopefully that would work. I'll copy it from here. No. Copy it from here. A new circuit would look something like that. Fits perfectly. That's how our new circuit would look. These are, we don't need these anymore. These are 3 resistors, and it's not R3 anymore. It's a new resistor, and we'll call it R245. Now it's the simplified version of 4 resistors, and let's calculate it over here. R2, 3, 4, and 5. It's the result of connecting 2 resistors in parallel. The 2 resistors are a 52 kilo ohm resistor and a 52 kilo ohm resistor. Wait, again we have 2 resistors, equal resistors connected in parallel. That's the simplest formula that we have. Equals, therefore it equals 52 divided by 2. That would make a 26 kilo ohm resistor. Therefore this one equals 26 kilo ohm. Okay, we're almost there. What would be our last step of peeling this onion? Looking at the simplified circuit C, we see that we now have simply 3 resistors connected in serial. You can see one connected to the other, no parallel connections at all. That would be an easy one, connecting 3 resistors in parallel. Let's make some room for our last step. Let's call it D. And that would be a pretty simple circuit. A battery and a single resistor that would represent all of the resistors that we had until now. Therefore we'll name it R1, 2, 3, 4, 5, and 6. And what would be its value? Well, simply the addition of R1, R2, 3, 4, 5, and R6. Oh, I forgot this is R6. And that would be 20 plus 26 plus 4 kilo ohm. That would give us 50 kilo ohm total. So the equivalent of all of this circuit, our equivalent would be 50 kilo ohm. Pretty simple circuit. So there we have it. That's the answer that we were looking for. The whole complicated circuit can be represented by a single resistor with the value of 50 kilo ohm. I'll just write this here, so you have a full view of the result. Okay, so let's move to number 2. What's the current flowing in this? What's the current flowing in this circuit? Well, here the simplified circuit D gives us a very easy way to calculate the current in this circuit using Ohm's law, because there's just one resistor here, one resistor, one battery. What would be I? Yep, simply I equals U divided by R, and we have U equals 100 volts. R is a single resistor that equals 50 kilo ohms, and that gives us 2 milliamps as a total current. Okay, before we continue to the last stage of the question, I want to give you a small tip that might simplify even the toughest questions. Whenever you get a new piece of data, a new result, for example, this 2 milliamps that we have here, any new piece of data, deploy it throughout the circuits that you have drawn. That might seem weird at first, but would become very useful later. So we found these 2 milliamps. Let's deploy this value throughout our circuits. This is 2 milliamps, and this is 2 milliamps, and this is 2 milliamps, and also this one. Okay, moving on. The last part of the question number, part number 3. What's the voltage between A and B? In order to find the voltage between A and B, we'll browse between the circuits that we have, and we'll see that if we look at circuit C, points A and B are, or calculating the voltage between A and B is very straightforward. Looking at circuit C, so let's write using circuit C, the voltage between A and B would be the current that flows between A and B times the resistance between A and B. And using Ohm's law would be V would be I total times R 2, 3, 4, and 5. That would be 2 milliamps times 26. That would equal 52 volts. And again, I'll deploy this data throughout the circuits. We found that this equals 52 volts, and we have A and B also here. That's 52 volts, and we have A and B also here. That's 52 volts. Okay, let's move to the next part of the question, finding the voltage between C and D. Let's browse between our circuits and see where what would help us here. Looking at circuit A, we see points C and D standing out. If only we could find the current flowing through this branch, then we could use Ohm's law and find the voltage over this resistor. That would be the voltage between C and D. But how can we find how can we find this this current? Let's call it I2. Maybe there's another circuit that can help us finding this current. And browsing again between our circuits, we see that this branch this branch here is exactly the same branch here. But does that circuit help us find the current here? Well, it does. We're looking for this current. We called it I2. And we see that in this circuit B, that the voltage between A and B is exactly the same voltage as you get here. These are parallel branches, so we get 52 volts here as well. And if we have 52 volts here, we can calculate the current through R2, 4, and 5. Let's write it down. I think we have the solution. So using circuit B, we can find I2. I2 equals the voltage over R245, voltage over R245 divided by the resistance R245, and that's easy. That's 52 volts divided by 52 kilo ohms. That gives us 1 milliamp. And remember what our rule: whenever we get new data, we deploy it throughout our circuits. So we now know that I2 equals 1 milliamp. I2 equals 1 milliamp, and this would help us. Let's see if we can get squeeze a bit more space out of it. Yeah, so now we can use circuit A to calculate the voltage over R45. So using circuit A, we calculate the voltage between C and D. That would equal the voltage over resistor R45, and that would be I2 times R45. That would be 1 times 4, and that equals 4 volts. Okay, by now we have the circuit's equivalent resistance. We have the current, the total current. We have VAB, that's here. We have VCD. So what's missing now? Let's move and see the question. The only thing that's missing for us now is the voltage between A and D. The voltage between A and D. Let's see what does that mean. We look at circuit A. They're asking us for the voltage between A and D. Is there a circuit in which this stands out more clearly? Well, yes. If you look at circuit B, and I'll write point D here as well. What they're asking us is the voltage between this point and this point, and the only resistor between these 2 points is R245. So the voltage between A and D is the voltage over R245, but we already know this voltage. The voltage between R245 is exactly 52 volts. So VAD is exactly 52 volts. So let me write down this last result that we have. we saw using circuit B, we see that VAD equals V245, and it's obvious that it equals 52 volts. That's it. Well, let's have an overview of everything that we did. This took a bit more time than I thought it would, but we did a lot of work here, and I hope we understood a few things that we did not understand at first. Let me give you I think the three main takeaways from solving this long question. One of them, peel the circuit like an onion. The second, keep the different layers of the onion while you peel it. And the third one would be, write down any new piece of data that you get on your way, distribute it throughout your circuits. That's it. I'll see you in the next videos. Thanks for watching.